Thanks to climate change, it's getting warmer almost everywhere on Earth, and that includes the Arctic. But if we look at the difference in temperature at a map, so if we look at how much warmer did it get comparing today to pre-industrial times, then we see the temperatures increased much more, so much stronger in the Arctic than compared to the rest of the Earth. That's called Arctic amplification. So, ironically, you could say the Arctic is quite the hot spot for climate change. Which naturally brings the question, why? Hi, my name is Nina Mahendler. I'm a doctoral researcher at Leipzig University and I do videos about Arctic science, especially about clouds and snow. And today I want to talk about Arctic amplification and feedback processes that are interlinked with it. So as I spoiled already, the answer to why the Arctic is warming so much faster than the rest of the world lies with feedback effects. By feedback, I mean some kind of process having some kind of effect, and that effect in itself then influencing the original process again, either strengthening it or weakening it. For example, temperatures in the atmosphere increase due to an increase in CO2, because we humans put a bunch of CO2 into the atmosphere. And that increase in temperature in the Arctic leads to a melting of sea ice. Now, when there's less white sea ice and more dark ocean, you can compare to wearing a white t-shirt in summer versus a dark t-shirt. The dark one gets much hotter, and so does the dark ocean. This in turn then leads to an increase in temperatures, so a positive feedback. This is called the so-called ice albedo feedback. So to repeat, we have warmer temperatures. Warmer temperatures mean less sea ice. Less sea ice means more dark ocean, which absorbs more heat, so warms much more, and therefore leads to an increase in temperatures again, which again leads to a decrease in sea ice. The term albedo is the sciencey word for ability to scatter back light. So lighter surfaces have a higher albedo, therefore scatter back more light, and more sunlight that's scattered back into space means less sunlight available that could be turned to heat at that surface. Darker surfaces have lower albedo, so they basically keep more of the sunlight for themselves, absorb it and turn it into heat. Besides the ice albedo feedback, there are other feedback effects that complicate the situation about climate change in the Arctic. There's lapse rate feedback, water vapor feedback, cloud feedback and Planck feedback. At least these are the kind of major contributors that I want to explain in today's video. Not all of the feedback processes are positive, so not all lead to a strengthening of the warming. Some can be negative as well. For example, the cloud feedback, there it depends whether clouds lead to a stronger or a weaker warming depending on the season. But let's break down each of the feedback processes that I mentioned already so that you get a clearer picture of what's really happening when we talk about the Arctic is warming so much faster. Let's start with the lapse rate feedback. Lapse rate describes the kind of rate at which the temperature changes in the atmosphere with an increase in the altitude. So typically it's much warmer close to the surface and then the temperature decreases if we go up in the atmosphere, but that's not necessarily the case. For example, maybe you've experienced in winter that sometimes it can be warmer up when you go up on a mountain. The Arctic has a very stable atmosphere, meaning there's very little air masses that get exchanged, as opposite to the tropics, where there's a lot of air mass exchange. So you have these warm air masses at the surface and warm air rises, so a lot of air that gets exchanged in the atmosphere. What that means for climate change, so for a warming effect, we can visualize by thinking about a pot of water. So let's take our pot of water, put it on the stove and turn it on. Then you get hot water, it starts to boil, and a lot of heat gets released, so a lot of energy escapes through warm, moist air. And that's the case in the tropics. So you have these warm air masses down at the surface which rise up, kind of bring the heat with them. So we have a negative feedback loop. The more it warms, the more the warm air masses rise and kind of bring the heat away from the surface. The opposite is the case in the Arctic. There you have this very stable atmosphere and the warm air close to the surface is trapped there. So if we have an increase in warming, then the warm air masses stay at the surface and warm the surface further. So we have a positive feedback loop. So far we talked about ice albedo feedback and lapse rate feedback, two positive feedbacks. There's a third one in the bunch, which is the water vapor feedback. Without going into too much detail, warmer air can basically contain more water in form of water vapor, as opposed to cold air. That's something we all experience. For example, I'm sure you felt a hot, humid summer day, but not a cold, humid winter day. Typically in winter, when it's cold, the air is more dry. Water vapor molecules in the atmosphere interact with the sunlight, similar to our black t-shirt or the white ice, or rather the black ocean. They also absorb some heat from the sun, and when they emit it again, they warm the surrounding atmosphere. So if we have warmer temperatures, we have more water vapor molecules available. More water vapor molecules can heat the atmosphere more, so lead to a further increase in temperature. Further increase in temperature means more water vapor, and you get where I'm going with that. So we have again a positive feedback. Currently it's not clear whether this water vapor feedback affects the tropics more strongly or the Arctic. There's different studies reaching different conclusions on whether that's a big player in Arctic amplification or not. So, subject of ongoing research. That brings me to the cloud feedback. Here the situation gets even more complicated because there the effects of whether it's a positive feedback, strengthening the warming, or a negative feedback, weakening the warming, depends on the seasonality. So it depends whether we're looking at polar day, where it's light the whole day, the sun never sets, or whether we're looking in winter and polar night, when the sun never rises, it's dark the whole day. So clouds, just like our t-shirt or the ice or the water vapor molecules, they interact with the light from the sun. They typically have a pretty high albedo due to their light color, and therefore scatter back a lot of light. Scattering back a lot of light again means there's not that much available to transform to heat, so rather a cooling effect. That's the case in summer. So in summer, typically clouds have a cooling effect, so they weaken warming. In winter, however, the sunlight is absent. Remember, the sun never rises above the horizon during polar night. There we have heat though from the surface. So the Earth also in summer emits heat from the surface. However, the effect from the solar light, from the solar radiations, or from light from the sun, is much stronger. In winter that's not here, so we only have the heat from the surface, and that can get basically trapped by clouds, which act as almost a shield or an umbrella, keeping the heat at the surface and therefore leading to a warming effect. So in winter, we typically have a positive feedback loop. Situation gets more complicated because it also depends on exactly what surface is underneath, how high up are the clouds, what are they exactly composed of. Also, how cloud properties and cloud occurrence will change in a warming climate, still subject to ongoing research. I myself am studying cloud processes at the microphysical level, so looking at the tiny ice crystals that the clouds are composed of, so I'm quite passionate about this subject. But before I go on longer, let's go to the last feedback that I mentioned in the beginning, the Planck feedback. And here I have to admit, I had to look that one up myself because I was like, oh, what was that again? But no surprise, it's about the Planck effect, which you might remember from some kind of physics lectures in school. Basically states that as the temperature of a black body increases, the amount of heat that it emits increases to the 4th power of the temperature. So the temperature multiplied by itself and itself and itself. So as we increase the temperature, there's a lot more heat that gets emitted. Now, don't focus on the black in front of black body, because approximately the Earth itself could be seen as a black body. So as the Earth itself heats up, it also emits a lot of heat. So there's less heat available to warm it further, and we have a negative feedback loop. However, that does not only affect the Arctic, but the whole Earth. So to sum up, the feedback processes that especially affect the Arctic are almost all positive, which explains that the Arctic is warming much stronger than the rest of the world. Because this warming happens so fast, it can be quite devastating to the local ecosystem. Now, I'm not a biologist, so don't quote me on that, but I, for example, heard that reindeer can have it quite tough. For example, when it thaws too early and then freezes again due to temperatures just dropping below zero slightly, then they can't really dig through the ice to reach to some kind of food sources, as opposed to if it were cold the whole time, then there would be just snow and they could dig to find food. Also, we should not forget that the warmer Arctic also affects weather in mid-latitude, so here in Europe or in the US. But I'm gonna stop here for today. I hope you learned something new, got some enjoyment out of the video. Leave me a like and a comment. If you want to encourage more videos, subscribe to this channel. Stay safe. I hope you have a lovely rest of the week and see you soon. Bye bye.